Section 1.6 is on page 60. Talks about nested quantifiers. Nested quantifiers is when one quantifier is within the scope of another. So in this section, we're going to start really getting to actual statements and check if they're true or false. And pretty soon we're going to start doing proofs. So this is all building toward making official proofs. So on page 68, I'm looking at number 2. It says translate these statements into English where the domain of each variable consists any real number. So first one says there exists an x such that for all y, x times y equal y. So there exists an x. Well, yeah, that is true. If you let x equal 1, then y equal y all the time. So this is a true statement. B says for all, or let's say for every x, for every real number x and for every real number y, if x is bigger than or equal to 0 and y is less than or equal to 0, so this is positive or 0 and this is negative, then if you take the positive or the 0 minus the negative that's always positive, that's true. Even if it shows x to be 0, since y is negative, that's going to always be true. So C says for every x, for every real number x and for every real number y, there exists a real number z such that x equal y minus z, or simply z equal x minus y. That is true. Choose any two numbers you want and we could choose z to match. That's fine. Number 4, same page. Let P of xy be the statement. Student X has taken class Y. So that's what P stands for. Where the domain X consists of all students in your class and Y consists of all computer science courses at your school. Okay, so Y is computer science courses at the school, all of them, and X would be all the students. Express each of these quantifications in English. So this says, well, in English, some students in your class has taken some computer classes, computer science classes. Versus if you just change that right there. This says, so remember, x, y, x will be all the students x has taken this class y. The domain is all students in the class, and this is all computer science classes. So B says, there is a student in your class who has taken every computer science class. C, well, not every student in your class has taken, instead of saying some or taken, you would say at least one. At least one to make it official. So when we get to the time to the proof, all what you have to show, to bring a counterexample to show that's not true. Here it says there is a computer science class that every student in your class has taken. You could say all, but we're going to go with every. That's better. Here, why was every computer science course has been taken by, well, instead of some, at least one student in your class. And here it says every student in the class has taken every computer class, every computer science class. Keep on forgetting the word science. Number 6. That's too many of those, but it's all good. Let's see if X means that student X is enrolled in class Y. Domain consists of all students in a class and in your school. And the domain of Y consists of all the classes being given at your school. Express each statement by a simple English sentence. So we use C here. A says RG is enrolled in CS, Computer Science 252, or whatever that is. Now, here it says someone is enrolled in Math 695. Here it says Y was, here it says Carol, or CS is enrolled in some courses. D, some student is enrolled in Math 222 and Computer Science 252. There exists, let me see, E. Okay, X not equal. There exist two people, two distinct people. So X not equal Y. There exists an X and a Y, but they're not equal. So there exist two distinct people, different people. There exist two distinct people. Let's see. Let me erase that. Let me just read that one more time. There exist two different people or distinct people, and the second of whom is enrolled in every course that the first is enrolled in. So if the first is enrolled in a class, the second is enrolled in that class. You could say that too. So you could say there are two distinct people, and if the first is enrolled in a class, then the second is enrolled in a class as well. Last one says there exist two distinct people who are enrolled in the same courses. So this runs back and forth. There exist two distinct people who are enrolled in exactly the same courses. Whenever one of them is enrolled in the class, the other one is, and vice versa. Okay, this one states, let f, the function f of x, state that x can fool y. Anytime you use that, first can fool the second. Where the domain consists of all people in the world, use quantifiers to express the given statements. Okay, everyone, so let's say everyone can fool Fred. All right. Evelyn can fool everyone, so any y that you choose, Evelyn can fool them. Everybody can fool somebody. So everybody, there exists somebody such that they could fool them. There is no one there exists no one that can fool everybody. E, no one can fool both Fred did I miss one? No. There is no one that, okay, this one's right. E, everyone, okay, I skipped one. I seem to do that now. Everyone can be fooled by someone. Everyone can be fooled by someone. Someone means some. Okay, there you go. And you could apply it now. So everyone can be fooled by someone. Good. F, no one can fool both Fred and fool Jerry. All right. Nancy can fool exactly two people. So you're going to choose exactly two. There exists one person and another person such that Nancy can fool the first person and fool the second person. But now you want to make sure that they're different. There's more to this. Nancy can fool exactly two people. So if I chose there exists one second for first, and those are not equal. But she can fool exactly two persons. So, and for any y, if Nancy is to fool y, then y would be either the first one or the second person, because these are the only two people she could fool. All right. No one can fool himself or herself. So there exists no one that can fool themselves. There is someone who could fool exactly one person. Okay, now get beyond that. Besides him or herself. So if we chose a person and that person, we want the exactly one now, and the fooling does happen. And for anybody else, if the fooling does happen, oops, XC first, X, the fooling does happen, and that's not himself, then that must be one person, exactly one person. Yeah. Same deal. Express each of these statements using predicates, quantifier, logical connectivity, the traditional, and mathematical operations where the domain consists of, here we're talking about only integers. So A, the product of two negative integers is positive. if you choose any two integers, let the first one be negative and the second one be positive, then the product is always positive. Now, the average of two positive numbers is positive. Alright, again, for any two numbers that you choose, if the first one is positive and the second one is positive, then the average of the two is always positive. The difference of two negative integers is not necessarily, it's not always positive. The difference of two negative integers is not necessarily, so it's not always true. That's what it's saying. So there does not exist, so it's not for all, that's what this is saying. It's not that for all numbers, for the first one is negative and the second one is negative, then the difference is negative. Thinking just if did this correctly. Yeah, I think so. Thinking of another way of saying that, I could also say the difference of two negative integers, not necessarily. So there exists some x and some y, such that if x is negative and y is negative, and the difference would be positive. So that's also the not necessary part. The difference. So there are some numbers in which if they could both be negative and the difference is positive or zero. D. The absolute value of the sum of two integers does not exceed less than or equal to the sum of the absolute value. Okay, so here it's saying for any x, y, absolute value of the sum does not exceed the individual absolute values. Alright. So here you're not saying not for all, and here you're saying there's some. That's pretty much the same analogy. Now if I look at number 22, usually the predicates quantifiers look the same thing and use mathematical operate to express the following statements. Okay, there is a positive number. There is a positive number that is not the sum of three squares, three numbers for all A, B, C. If this is a positive number, x would not equal the square of those three. Remember, the domain consists of all integers. I have not been putting lines through those. Oh boy. Okay, let's do that really quick. It doesn't want to register. Keep changing the color of the line. It keeps coming green. Okay, here we go. All right. Now let's look at 26. Let Q be, okay, so Q is the statement, x plus y equal x minus y. So the x's cancel out. This is really saying y equal negative y. If the domain, okay, integers only. So 1, 1, if you put x1, y1, this would mean that 1 equal negative 1. This is false. So again, you could use this, or you could just look here. When the y equal itself, x will cancel out. B says, if x is 2, then y equals 0 is a solution. Well, yeah, that's right. 0 equal negative. That is true. Right? Or you could say 2 plus 0 equal 2 minus 0. Doesn't really matter. But here, 1 plus 1 does not equal 1 minus 1. That's not true. C, if I let x equal 1, no matter what x equal, y would equal, and that is, oh, it says for all y. Well, for all y, those are not equal. This is false, right? Not for all y. For some y, yeah. You know, so namely y equals 0. D, for all x, I'm sorry, not for all x, for some x, this y equal 2 will work. Well, 2 can never equal negative 2. This is false. And how about E? E says, for some x, for some y, that is true. That's right. X could be anything, doesn't really matter. But if I let y equal 0, any x you want, let y equal 0, that's going to be true. Here it says, for all x, that's right. X doesn't really matter here because x is irrelevant. It's going to cancel out. There exists a y such that this is true. Well, yeah, that's true as well. Let that be 0. So you notice the difference between some and all. G, for any value of y, no, not all, I'm sorry. For some value of y and all x, this could be true. Yeah, that is true. Because for some value of y, let y equal 0, and any x you choose, this is going to be true. And if I reverse the order, for any y, there exists an x, that's false. Let y equal anything, any x you want. Let y be any number other than 0. 5. 5, 0. So 5 does not equal negative 5. And I, for all x and all y that's new, of course that's false. X really doesn't change much. It's just the y you gotta be really careful about. Now, counterexample is when you give a statement that is counterexample when you give a statement that negates what they're trying to say. If possible, to these universal k, domain will be all integers. So this says, for any x that you choose, there exists a y such that x equal 1 over y. All integers. Well, that's not true. That is false. Let x equal 5. 5 equal 1 over y. So y must be 1/5. That's not an integer. You could choose 2, you could choose 3. Just don't choose 1. Because here they said for all. If they said unique, then yeah, we could say, well, alright, let x equal 1. That will work. B, for any x that you choose, there exists a y such that this is true. So it says, for any x, there exists a y that this is true. And if I think about this, for any x that I choose, there exists a y. So that would be, let me think. But y is always positive because it's a square. If I let x be a negative number bigger than 100, say negative 110, then this says negative 10 is bigger than y, so this is false. Right? Let y be whatever it wants. Choose x to be 110, 120, 105, 101. Well, if you put a 101 there, I'm sorry. if you let y equal negative 110, then negative 10 cannot be bigger than a positive. That's not possible. And C says for all x and all y x-ray, of course not. That's not true, you know. Choose x to be, they're not equal. Choose 1 and 1. That wouldn't work. That'll be a counterexample. We could also choose 0. 0 squared does not equal 0 cubed. That's not true. 0 equals 0. This is for all, not for some. So that is definitely false. Now we summarize those in a table. That's from the book. You could find it in the book. And they talk about one is when you say for all, when you say for all and some and all, and those are not the same, by the way. And here when you say for some of each, they tell you one is a true and one is a false. You should review that. And that's pretty much it for this section.